Welcome back to G Fun Facts Online, the place where we explore the most mind-blowing science and tech. Today, we're diving into a world that sounds like something straight out of a sci-fi movie. Materials that can think, heal themselves, and adapt to their surroundings. No, I am not kidding. We're talking about dynamic covalent chemistry, or DCC for short. So what's the big deal with DCC? Imagine materials that are alive, in a way, not breathing and eating, but living because they can respond to their environment, repair damage, and even be recycled more easily. This isn't magic, it's clever chemistry. At the very heart of these intelligent materials are something called dynamic covalent bonds. Think of them as super smart molecular handshakes. Unlike regular, super strong handshakes that are hard to break, these bonds can break and reform. They can do this over and over, often triggered by things like a change in temperature, a flash of light, or even a shift in pH levels. That's acidity or alkalinity. This ability to break and remake bonds is what gives these materials their superpowers. For example, there are imine bonds, which are great for making self-healing hydrogels. Imagine a jelly-like substance that fixes its own cuts. Then there are disulfide bonds, often used in recyclable plastics, allowing them to be broken down and reformed. Diels-Alder reactions are another cool type, which are reversible with heat, meaning you could have materials that mend themselves when you warm them up. And there are boronic ester bonds that react to pH and sugars, perfect for sensors, and even special hindered urea bonds that help materials self-heal even at cooler temperatures. Now, let's talk about one of the most exciting applications, self-healing. Picture this. You scratch your phone screen, and instead of a permanent mark, the screen slowly mends itself. That's the promise of DCC. When a material with these dynamic bonds gets damaged, the bonds can reform across the crack or scratch, essentially stitching the material back together. Sometimes this happens all on its own, and other times it needs a little nudge, like some heat or light. Scientists have even made polymers with these special urea bonds that not only heal physically, but can even restore electrical conductivity after being damaged. How cool is that? But it's not just about healing. DCC creates materials that can adapt. Think shape memory. Imagine a material that you can crumple up, but when you apply a trigger, like heat, it remembers its original shape and springs back. Dynamic bonds make this possible by allowing the material's internal structure to rearrange and then lock back into place. These materials can also be stimuli responsive. This means they can change their properties, like how stiff they are, how much can pass through them, or even their color when their environment changes. This opens up amazing possibilities for smart sensors, targeted drug delivery systems where medicine is released only where it's needed, and responsive coatings that can react to their surroundings. And here's a huge one for our planet: reprocessability and recyclability. Many plastics, especially tough ones called thermosets, are very difficult to recycle because their chemical bonds are permanent. But with dynamic covalent chemistry, we can create what are called covalent adaptable networks, or CANs. These materials can be broken down into their basic building blocks and reformed, making them much more sustainable. It's like having Lego bricks that you can take apart and build something new with, over and over again. The field of DCC is moving super fast. Scientists are working on making these materials even stronger while keeping their amazing dynamic properties. They're also focusing on green chemistry, using ingredients derived from plants instead of oil, and designing materials for perfect closed-loop recycling. New types of reversible chemical reactions are being discovered all the time, expanding what's possible. We're seeing DCC used to build incredibly complex tiny structures, leading to completely new functions. And the applications? They're everywhere. From biomedical devices like scaffolds for growing new tissues or smarter drug delivery, to soft robotics that can move and adapt, advanced coatings for cars and planes, and even aerospace components. Recently, researchers have even used disalinide dynamic bonds to create shape memory polymers that can transform from a flat 2D sheet into a complex 3D shape just by programming them with light. Of course, it's not all smooth sailing. There are challenges, like making sure these bonds break and reform at just the right speed, figuring out how to make these materials on a large scale, ensuring they last for a long time, and fully understanding how their tiny molecular design leads to their amazing abilities on a larger scale. But despite these hurdles, dynamic covalent chemistry is paving the way for a new generation of smart, sustainable, and high-performance materials. As we learn more, we can expect even more sophisticated materials tailored to solve some of our biggest global challenges. Materials that heal, adapt, and respect our planet. The future is truly dynamic. That's all for today on G Fun Facts Online. Join us next time for more amazing insights into the world around us. Thanks for listening.